might just keep you guys for an hour based on the number of persons that would be here. All right. So, Archimedes principle. What in the world is that? So pretty much it talks about when give me a second, when a body is partially immersed in a fluid or fully immersed in a fluid, it's gonna displace the amount of water due the amount of water displaced is gonna be equal to the upward force. What does that mean? What does that mean to you? Um, let me go to my paint. I think going to paint would be a better scenario than this one. So I can make some pretty drawings. Not working for me. Oh, that I just passed you guys. Where are you? Where are you? That's where you are. Alright, cool. Couldn't find it, guys. Okay. So let's look at it in terms of an experiment. Um, let's look as a scenario. Scenario one. I have a stone and I put this stone on a balance, on a spring balance, and the spring balance in terms of the weight of the stone will tell me that hey, the stone is 5 newtons in air. Now if I then same spring balance and I put the stone in water, for argument's sake, um I'll get 3 newtons. So pretty much if I'm gonna draw a diagram, we know that we had a 5 newton going here and why this became 3 newtons. It means that I had 2 newtons going there, going upwards. With 2 newtons going upwards, our resultant force would have been 3 newtons going downward. Now, what Archimedes principle says? Archimedes principle says that if I, for argument's sake, had a stone and I put it in, for example, a eureka tin and allow water to be displaced from its tin and I collected the water, the mass of this water would have been equal. So if I put the mass of this water and I weigh this water, for argument's sake, it would have been um, roughly equal to 2 newtons. So that's about 200 grams. Yeah, that's about 200 grams, I think. And that's what Archimedes' principle states, that when you put a fluid inside, when you put a fluid when you put an object inside a fluid, it's going to experience an upward force. And if you allow the water to be displaced, the upward force of 2 newtons would be equal to the weight of the water displaced. And that is Archimedes' principle. Hope that makes sense to you. All right. Um, okay. So that's what he's saying in his experiment. All right. We take it a step further, and if we were supposed to calculate options, I'm gonna pretend that CXC said that we're not gonna derive um this formula, and if we want to calculate it, we use this formula. We use the density. So this is gonna be density times gravity times height, or density times gravity times volume, and that would be equal to the weight of the water displaced. So you can go ahead and make a note of that. So we're looking at Archimedes' principle, and let me see if we have a definition. Uh, we're just gonna define. Let's define it. So Archimedes' principle, you're gonna make a note. Archimedes' principle states that when a body is totally or partially submerged in a fluid, it experiences an upward force which is equal to the weight of the water displaced. And if you want to calculate the upthrust, this would have been your equation. So make a note of that equation and that definition. Give me a second.
My grandma has a fancy ring.
Let me know when you finish. Give me a thumbs up when you're finished with that. Give me a thumbs up when you finish making a note of what is Archimedes' principle, as well as taking out that equation. Any thumbs up? We finished with making a note of what that is? Archimedes' principle as well as the formula for upthrust. Smart, awesome, good. So make a note of that. So we're gonna look at what we call resistive forces. So pretty much the concept of resistive forces, they're gonna cause something to slow down, or it should prevent it from moving. And we need to know about resistive forces. One of the resistive forces, we're gonna keep all this mumbo jumbo. And one of the resistive forces that we're gonna talk about is drag, and it is also known as air resistance. And we'll experience this. For example, you're in a car, and what's gonna happen is that when you're in the car and say stick your hand out and the car is traveling slowly, what happens is that you're gonna feel the air resistance on your hand. The faster you're traveling is the more force you feel in your hand. So if you notice that the equation here is gonna be different. If you read it, it talks about an object traveling at a faster rate. The the in terms of your resistive force, the formula is gonna change from F is gonna be equal to the constant times velocity, or F is gonna be equal to the constant times velocity squared. Because when you move at faster speed, you're gonna experience more air resistance, and that's wonderful. And it's the reason why a raindrop don't bust head. Because by right, a raindrop should bust head. You guys know that, right? Hello? Edwards, you know that the raindrop by right raindrop should bust it, right? No. All right. Yes. What do I mean? So this is what happens. When you're looking on, let me show you. When you're looking on a raindrop, oh sorry, I didn't tell you this. A fluid can be a gas or it can be a liquid. So when we talk about Archimedes' principle, that anything in a fluid is going to experience an upward force. Um, yeah, once you're moving vertically, you're going to experience a form of upward force. So this is going to be my raindrop. By right, when the raindrop leaves the cloud, it's gonna the mass of the raindrop. You're gonna move in terms of mass times acceleration due to gravity, or that we can call it our weight. What's gonna happen now is that when it's moving downward, it's gonna experience an upward force called your upthrust. Now, there's another force. There's called the drag force, which is right here. The drag force will be upward, but when it just start move, what's gonna happen is that the raindrop won't be moving very fast because it just start to move. What's gonna happen now at a point of free fall, your weight, your upward force, let's call this F up, and your drag force are gonna cancel out each other. So what's gonna happen is that your upthrust plus your drag force is gonna be equal to the weight. Therefore, the net force on the object, net force, complete force, the net force is equal to 0. Now, some fool people might say, but wait, sir, if the net force on the raindrop is equal to 0, that means the raindrop not gonna move. No, the raindrop are gonna move same way, but it's gonna move at what we call a constant velocity. And this constant velocity is called terminal velocity. So what it means is that the raindrop will no longer accelerate downward but move at the same velocity for the entire journey. So if so the raindrops are not allowed to accelerate from the top of the sky into the ground, because if they were allowed to accelerate, we couldn't stop them. So let's start. What's gonna happen when a raindrop is in a fluid or in air? It's gonna experience three forces. It's gonna experience the weight. It's gonna pull it downward. It's gonna accelerate downward. It's in a fluid. Gas is a fluid. It's gonna experience an upward force, and it's gonna experience a tiny drag force. When an object moves quicker, like if you put it on outside of a window and you're moving faster, the drag force is gonna increase. When the two forces, when the upthrust and the drag force is equal to the weight, your net force is 0. And when your net force is 0, you travel at terminal velocity, which is a constant velocity. What does this look like in a graph? We're gonna do a question. What does this look like in a graph? This is a graph for terminal velocity. What's gonna happen is that the object is gonna move off quickly, it's gonna accelerate, and as it starts accelerate, it's gonna start to pretty much slow down. And when it slows down, it's gonna then travel at that constant velocity. And that's gonna answer your homework question that I gave you. And it's gonna become terminal velocity. And it happens when your upward force is equal to your downward force. So let me give you, you're gonna draw this here. You're gonna need to make a note. So if you're looking at a graph and you want to know the terminal velocity, this is what you look at. You can, so let's see. I want to give you something small to write. All right, don't worry. Just draw the. Let me see if I can give you a definition. All right, write down this definition. At terminal velocity, the weight of an object is equal to the drag force, the resultant force is zero, and no acceleration. And that is important. An object reaches terminal velocity when it falls through a liquid. Question: do human beings experience terminal velocity when they free fall? Hello? If you're supposed to jump out of a plane, do you experience terminal velocity? You can ask Google. Hello? Hello? Answer is yes. Back in the days in the 1990s, there's a movie on it called Terminal Velocity. So what happens is that if you ever watch skydiving and you're seeing they're flipping and they're gallivanting and the entire nine yard before they pull the parachute, they're pretty much waiting on it until they reach terminal velocity before they pull the parachute. So eh, yeah, that's gonna be a thing. So that skydivers use it, and as well as your orientation. What in the world do I mean? If you're lying down, that's the most of the time when you see skydivers, when they pull their parachute, their hands are up, their feet are up, and they're like almost lying down on their belly. That helps increase their drag force, and it helps slow them down to a point, and then that's when they pull their parachute. You don't see them looking like they're standing upright. Well, they're in the sky, but you're not seeing them upright. So they're gonna do that. So terminal velocity does affect all objects, but it takes a human being a minute to reach terminal velocity. So you have a free fall for a minute before you reach terminal velocity. The bigger you are is the longer it's gonna take for you to reach terminal velocity. So just make a note of what terminal velocity is, and remember, yes, when you reach terminal velocity, you still will be moving, although there's no force on you, but you'll be moving at a constant velocity, known as terminal velocity. Make a note of that, and then give me a thumbs up when you finish. Any thumbs up? All right. We can just. I think you guys have a graph already, and ooh, this is an interesting thing to do. All right. Give me a second. I'm going to need to look for something. Let me make sure you are seeing my screen. Oh, yes, you are. All right. Let's look at the terminal velocity question. By any chance, you guys draw the graph that I gave you? Let's see if I can. This is a perfect question. That is a perfect question based on everything. All right, look through that question, and I'm gonna come back to you. Can somebody take a screenshot of it and just put in the group for me, please? I don't see the screenshot. Thank you. Yes, I am recording the meeting. Um, I'm gonna. That's why I didn't want to change the screen. All right, thank you. All right, so let's look at this question. Love the question. Let's go back to the question. State Newton's laws of motion. We're gonna scrap that one. Explain why a small sphere released from rest at the surface to fall through liquid in a deep tank eventually moves at constant velocity. Sketch a graph to show how the acceleration of the sphere varies with time and as it releases through the surface of a liquid. Oh my God. Oh, still, that is a mouthful question. All right, let's get the show on the road. This is a wonderful question. This is a question we're gonna look at first. Um, we're gonna tell Newton to jump off a bridge. Why in the world can I? All right, let me bring that across. Give me a second. Yep, it's there. All right, so this is gonna be the question we're gonna look on. Um, so it says sketch and explain. All right, let's look at it. I'm gonna take it in steps. Ready? So this is what we have. This is gonna be an experiment that we'll be doing. I was looking at your school to see if you have a long enough tube. I want a long enough tube where a ball can reach terminal velocity in a fluid. So the other day I was laughing. That's what I was looking on. Give me a second. Hello. Good morning. Yes. All right. I'm recording the session. I'll post it tomorrow. All right. Um so this is it. The ball will be released in a fluid. It's more like we use marble or a steel ball. I'm gonna release it in a fluid. What's gonna happen is that initially, when the ball was not in the fluid, I'm gonna draw it stage by stage. The ball will be falling downward, and then when it's in the fluid, it's gonna experience an upthrust. So, a small sphere at constant speed. So, can I make a note of this? Initially, when the sphere sphere is released in the liquid, it will experience an upthrust, and its weight will pull it downward. All right, everybody got that? So that's what happened initially. So weight will pull it downward. Sorry about that. Now, what's gonna happen? As it falls, as it falls, you're gonna have the up thrust. It's You're gonna have the weight, and you're gonna have a drag force. And we're gonna have as it falls, the drag force will increase until the up thrust plus drag force is equal to the weight of the ball, of the sphere. At this point, the the net force on the sphere is 0. So what we're gonna have this. We're gonna have your up thrust plus your drag force is going to be equal to weight. When, and then we're going to use our terms. Terms. The sphere will fall at a constant velocity known as terminal velocity, since net force is 0. And that would give you pretty much your 8 marks. I'm not gonna be that worried. We're gonna have our drawings. I just draw. Maybe I put a little drag force up on this one, and then I draw this one, and then I would say that at this point I have terminal velocity. So I'll just start. I'll have 1, 2, 3. So at 3, it's gonna travel downward without any acceleration and travel at terminal velocity. So what's gonna happen is that as you move faster and faster, your drag force is what increase, and as your drag force increase, what's gonna happen is that your drag force plus your up thrust is gonna be equal to your weight, and the object will no longer accelerate downward and travel at a constant speed or velocity known as terminal velocity. And that's how I'd answer that question with my drawings as well. Take a screenshot of that and send that to the group as well, please and thanks. Are there any questions? All right, take a screenshot and send to the group. All right, thumbs up if we can move on to the other part of the question. All right, let's look at the other part. Other part of the question even nicer. Can you believe it? This question is one of the nicest questions you'll see in physics. All right, let's. Oh, are they dirty question this? All right, let me take this part first. All right, you know what? This is a mean question. I like it. I'm gonna ask you guys to draw the force diagram. The force is acting on this scenario. Read the scenario. Draw the force acting on it. I'm gonna give you what 2 minutes. Draw the force diagram. Just gonna draw a balloon and draw the direction where you think the forces are going. And there's a trick to the question. You guys want me to do the question instead? Thumbs up if you want me to do it. And do it. All right. So this is it. So we're looking on. Let me show you the trick. Oh, I'm on the wrong screen. The trick is this. It's a helium balloon. And helium weather balloons. Normally, when we look at terminal velocity so far, everything we're looking at was going downward. So your weight is going downward. Your up thrust is going that direction, and your drag is going that direction. And CXC would have tricked you if you have drawn that. That is the drawing you most people think, right? So there should be three forces. There should be three forces there. But no, this is where this would have been wrong if you have drawn that for helium balloon. Um, let me show you why it's wrong. Now, the helium balloon is gonna act like this. The helium balloon is so light, so your weight will be going down. That's correct. Your up thrust will be going up. It's gonna be more than a weight, so it's gonna travel upward. And your drag force will be going down when you start. Drag force is a resistive force, so therefore it has to go in the opposite direction from motion. So that's where most students would have made that mistake. Would you have made that mistake? Mm-hmm. Because your helium balloon is gonna be released into the air and it'll be traveling upwards. Eventually, your drag force is going to reach a point, and the helium balloon will reach terminal velocity. So draw a free body diagram to show the forces acting on the helium balloon, and that's how you answer the question. Make a note of that. Take a picture and send it to the group. Thumbs up when you finish. Ready? Next question. Maybe I shouldn't. Calculate the Archimedes principle. Use Archimedes principle to calculate the buoyant force. How would you calculate that? The buoyant force is equal to the upthrust. Remember that equation I asked you to take down. You have it. Ready? Hello? Did the guys take down the equation I asked you to take down? You have it down? Hello? Alright. So we know, and remember, what my equation again is. Okay. So we can say upthrust is equal to density times gravity times area times height, which is volume. This is volume. So we know the density is right here. We know gravity is 9.8, and we're told volume is 4 over 3 times pi cube. I'm getting this from here. What's R? Let me double check what's R. We're told the radius. Yeah, 2.5. It's 2.5 cube. Put that in a calculator and let me know you get, and that would have calculated your upthrust. And that would answer part 1. Yeah. Anybody? Anybody get it? I got 801. 801.68 newtons. That's all I got. Take a screenshot and you can send it across. Whoever can calculate terminal velocity now. What am I doing? Alright. Ready? Calculate part B. Okay, thumbs up, yeah. Now we know we're given this equation. Give me a second, let me write the equation. FD is equal to half pi r squared times density times velocity squared, which is this velocity is going to be terminal velocity. So we know the condition for terminal velocity is going to be this is the balloon. So we know that the upthrust should be equal to the weight of the balloon plus the drag force, which is going to be Fb. So we know the weight is going to be equal to mass, which is double check the mass. Mass is 15 kilograms. 15 times 1.8. I will know that Fd is equal to this equation at the top, so it's going to be half times 3.14 times 2.5 squared times the density of 1.28 times the terminal velocity squared. And we don't know what that is. I know that the upthrust was equal to 801.68 newtons. So take a note of that, and I'm gonna erase the top part and send that screenshot to the WhatsApp group. Are there any questions? Go ahead. Take it. All right. Mirang. I don't have my calculator, so I just rough calculate it. Did you cube it? I don't know. Where you use for your gravity 10 or 9.8? All right. Like I said, I know it's 800 and something, but I didn't use my calculator, just rough calculate it. So that could be wrong. But the principle of it works the same. Apart from that, you understand the principle why I said the upthrust is equal to the weight plus the drag force, right? All right. Um, calculate this part and tell me what you get. Put that in the calculator. What you get? Ah, 147? 15 times, yeah, 147. Yeah, What about the other part? Plus 1 point, what, 0.5 times, yeah. So add them together now, brother. No, fine. That's what me get when I rough calculate it. You guys, somebody tell us send a screenshot of the top answer already to the group. All right. Erase this, and I'm going to just divide both sides by zero. Sorry, it's gonna be 0.868 159.7 v squared divides both sides by 159.7, and v squared would have been equal to whatever is equal to, end up with 5.02, and I find the square root of that, and that's what I'd get from my terminal velocity. End up with 2.24 meters per second. All right, take a screenshot of that, and let's look at the last question on this section. All right. Um, how will you answer the last question? Ready? Thumbs up. Are you ready for the next part of the question? We're still writing. All right. Let's look. All right. I would use if I want time. Only equation I can think about now with time in it, given distance and acceleration, all these wonderful thing. I'll go to Newton's. I'm gonna assume you don't reach terminal velocity. X is equal to ut plus gt squared. When it just start moving off vertically, I'm gonna give its initial velocity as 0. It's gonna try. It's gonna have some inertia going there, so I'm gonna give this portion 0. I'm gonna 10, so it's gonna be 10 times. It's gonna be 10,000. So what 10,000 is. I don't know the time. I know gravity is 9.8. Should be negative, and I'm gonna find time. So it's gonna be half of this. Half of it's 4.9. Part of me thought I needed to know that. Divide both sides by 4.9. Therefore, t is equal to find the square root of, give me a second. I end up with a time of seconds. That's the time I end up with. Take a picture of that, and let me see if I can get you one more question. I gave you a question on terminal velocity already. Um, the graph one, you can complete that one. I'm gonna send it to the other group. It's a paper tree. It looks like a paper tree. After you're taking that down, let me know.